Hello friends, welcome to my channel. Let's have a look at problem 2226, maximum candies allocated to key children. In this video, we're going to explain a solution based on binary search, and also we will make some comments on the coding part. First, I'm going to look at the problem statement, and then we look at the example and analysis, and finally we share the code and explain it line by line. Let's first look at the problem statement. We are given a zero-indexed integer array called Candies. Each element in the array denotes a pile of candies of size candies I. We can divide each pile into any number of subpiles, but we cannot merge two piles together. So we are also given an integer key, which represents the number of kids or children. We should allocate piles of candies to key children such that each child gets the same number of candies, and each child can take at most one pile of candies, and some piles of candies may go unused. So in other words, we can use one pile to serve more children, but we cannot serve several more than one piles to a single child. So we are required to return the maximum number of candies each child can get. So here are two examples. In the second example, this is very special because the total number of candies is 7. The total number of candies is 7, but k is 11, so we cannot finish the allocation. So the output is 0 because we need all the children have the same number of candies. So this is example 1, which demonstrates us a special case or edge case. The first example, so we can output 5, right? So we have 3 children, and this so we can serve 5. We serve 5 out of 8, serve 5 out of 6. However, this problem is also this example is also special in the sense that here the length and the number of keys are the same. In this case, we just need to return the minimum, right? So here the constraints for the problem are the following. First, the list candies can be as long as 10 to the power of 5, all right, and each of the elements in the candies list is bounded below by 1, and the key is bounded below by 1 and bounded above by 10 to the power 12. This is a large number. So with that said, we are ready to do the analysis. So here I'm going to give a treatment based on binary search. So here we're going to do two things. So our plan. First, I'm going to define a Boolean function to produce order, or more precisely monotonicity. This enables us to do binary search. So in the definition of the Boolean function, we're going to take the problem logic into consideration. Next is the binary search part. For binary search, we are going to do 3 things. First, search range. Second, shrinkage. And finally, return, right? The proper return. So this is our plan. So next, we are going to look at coding, and in between, we explain the logic. Let's look at step 1, Boolean function. So I'm going to define a fulfill. So it accepts the n candies. So basically it says that we're going to return if each children can get n candies, right? In other words, if each child can get n candies, number of candies, right? Here actually we can assume n candies is greater than or equal to 1. if it's 0, actually we can treat that as a special case in this problem. So now first I'll write a longer version with early stopping to explain the logic. Then after we finish the coding, we'll comment to make it a shorter one. So first we will get n children served. Originally is 0, right? So we are going to iterate. So for y in Candies, right? So this y can be divided. If we want each kid has this number of Candies, we are going to compute how many children this y Candies can serve. So this is nothing but q. Let's write a dummy index, dummy variable. It's dev mode. Let's just use this maybe. N children. So we're going to increment by y integer division by n Candies, right? So if n children is already greater than or equal to k, so we're going to return true. So this is an early stopping condition. We do not need to finish the whole array if k is actually, if n Candies is small. So afterwards, if nothing returned, we're going to return false. So this is our Boolean function. So next, we're going to do a binary search. So before we do binary search, here first, if we do not want to think too deep, we can treat a special case. If sum of Candies is less than k. In other words, so if we want to allocate one candy to the children, it's still not enough. So we're going to return 0 in this case. This will make the candies we're going to distribute is at least 1, right? So now let me write the binary search. So this one, edge case. Now binary search. So here we want to find the max in Candies such that fulfill in Candies is true, right? We want to find the largest one. So this is an important one. So because when we write binary search coding, so if the problem is a maximization problem or minimization problem, it matters, especially for the writing the search range and the return. So here we are going to first finish one solution, then we are going to comment about this. First we can low and high, right? So low, currently I'm going to set it to be 1. Also we fulfill this one, right? In Candies is greater than or equal to 1. And also because each pal can serve at most 1 kid, so the high will be the max of Candies, right? And then we are going to do the binary search. So here I'm going to write while low strictly less than high. Then we are going to check fulfill. If fulfill. So here let's first write the middle. So because this is a maximization problem, I'm going to do this: high minus low, integer division by 2. This is going to be important, and in this version we cannot see its effect in a zooming in fashion, but we are going to comment this. So here notice that we are going to start from high to low. We high, then shrink half, right, from high to low. Then we're going to check if fulfill mid. If this is true, right, it means that we still hope the larger. So we're going to set low equals mid. We cannot set low to be mid plus 1, because if mid plus 1 is happen to be false, then if we go upward, so it's also false, right? So we exclude the true, the parameters for returning true. Else, so if this is the false, right? It means it's too small. Then we're going to set let's see, if this is true, right? We want find the larger ones. If it's not true, it's false. So we want to find the smaller ones. So high is going to be mid minus 1. Right. So now what we are going to return here is we're going to return. So here, let's see. This is true, right? So we are going to return high in this case. If fulfill is true, so we return this, and then let's check. Yeah, and also let's look at the generic case. Yeah, actually this problem, in this problem, we might be also return low due to our writing. Let's see. Yeah, but because when we look at the low always makes this fulfill true. So this is the one point we want to make. Another point we want to make is that the special case check. So actually here, let me copy this version so that we can keep one and then comment on another one. So we can mark this as version 1. And here we can include the edge case in the general binary search. So here first I'm going to delete this one, but I'm going to check this to be 0, and also I want to return high as I like. So let me first check if it works. Yeah, the reason it works, like for example in this case, right? So in this case, the sum of the candies is strictly less than the number of keys, so we need to return a 0, right? And in this case, why it's right? Because in this function we cannot allow n candies to be 0, otherwise we cannot do division here. But the thing is that if you look at examine this situation, so here originally low is so for example 2, I want to make some comments. So let's do it here maybe. For example 2, this is a special case. Then low is 0 and high is 1, right? And then because we iterate from upper to lower, so this difference, this is a high minus low, is 1. So if we do integer division of 1 by 2, and then we're going to get 0. So in this case, we're going to have mid equals 1. Because to fulfill 1, so because we are calling fulfill function with 1, is not true. So then we're going to have high equals mid minus 1. That is 1 minus 1 is 0. And in this case, we're going to have low equals 0, right? Let's update this. Low equals 0 and high also equals 0. Then we didn't enter this while loop. We actually exit this while loop. So we return high. This corresponds to 0. That's why we see in this problem, it's better to return high. And then so this is the one point. So notice that here the strict less is important, and actually it has a joint effect with this way of shrinkage. So this one is a shrinkage, right? So here we because this is a maximization problem, we are doing high and downwards, right? If we have minimization problem, typically we need to also consider if we want to do the shrinkage from low, then add half, or from high, down half. So this is one. With that said, I guess another thing we might notice is that we can simplify the fulfill function a little bit. So here, let's copy this second solution, and then let's do this. I'm going to write this in a shorter version. So I'm going to delete all this part and then just write using comprehension. So we're going to check y integer division by n candies for y in candies, right? But we just want to check if this is greater than or equal to k. However, this one we need to return, right? This is a short one. It's actually without this early stopping, right? Because this one sometimes we don't need to finish iterating over all the full list, but this one we always iterate over the full list. So here I also have changed the name. So let's do a check for the last format. Yeah, it passes a special case. Now let's look at the generic case. Yeah, it passes all the generic cases. I guess in this video, that's about it for this problem. And in this video, we shared a solution based on binary search, and we commented on several of the ingredients in the paradigm or the method. So with that said, I guess that's about it for this video.